Hey, good to see you again in this universe of bold questions and strange answers. Here, every fact hides a bigger story, and we're about to uncover it. A microburst of color snaps into place. Okay, let's slide straight into today's discovery.
Imagine building a machine so sensitive that it can sense space-time stretching by less than a 10,000th the width of a proton. Not a vibration, not a tremor, a literal distortion of reality itself. That sounds impossible. But engineers didn't just imagine it, they built it. And today, you're about to see how LIGO became the most precise measuring instrument humanity has ever created. In 1916, Albert Einstein predicted something strange. When massive objects accelerate violently, like black holes colliding, they generate ripples in spacetime itself, gravitational waves. For almost 100 years, this idea stayed theoretical, not because it was doubtful, but because detecting these waves felt absurd. By the time they reach Earth, they distort space-time by a fraction of a proton. So the problem wasn't just physics, it was engineering reality to behave. The universe is subtle. Earth is not. Oceans hammer continents. Wind shakes structures. Cars vibrate cities. Even distant earthquakes move the ground beneath your feet. Inside materials, heat keeps atoms in constant motion. Every one of these effects is vastly stronger than a gravitational wave. So LIGO's challenge wasn't amplification, it was silence. Silence in a noisy planet that never stops moving. At its heart, LIGO uses interferometry. Here's the idea. A single laser beam is split into two. Each beam travels down a separate 4-kilometer arm. They bounce between mirrors many times, effectively extending the distance. When the beams reunite, they interfere. Sometimes constructively, sometimes destructively. This interference pattern is exquisitely sensitive to distance. If space-time stretches even slightly, one beam travels just a tiny bit farther. That change shows up instantly in the light pattern. That's the measurement. Now imagine firing a laser through air. Molecules collide with the beam. They scatter light. They add noise. So engineers built one of the cleanest vacuums ever achieved on Earth. Nearly 40 kilometers of stainless steel tubes. Inside, the pressure is far lower than atmospheric pressure, lower even than most regions of outer space. Space isn't truly empty. It still contains particles, just very unevenly distributed. LIGO's vacuum, by contrast, is carefully controlled, predictable, quiet. Because when measuring spacetime itself, random air molecules are pure chaos. Next challenge, the ground. The mirrors must not move. So they don't sit on solid platforms. They hang from multi-stage pendulums, a passive isolation system that naturally filters vibration. But that's only half the trick. LIGO also uses active isolation. Sensors detect ground motion in real time. Actuators apply counter-movements instantly. Passive systems soften the shaking. Active systems cancel what remains. Together, they reduce ground motion by factors of millions to billions at the frequencies LIGO cares about. The mirrors experience a quiet Earth that doesn't really exist. Now the mirrors. They're polished to near atomic perfection, but there's a subtle problem. Light carries momentum. When photons reflect off a mirror, they exert radiation pressure, a tiny force. At this sensitivity, that force matters. So engineers carefully balance mirror mass and responsiveness. Heavy enough that light can't easily push them around, but not so heavy that the system loses sensitivity. This is precision engineering at a philosophical level, when even light pushes back. Heat is everywhere. Atoms vibrate, materials flex. Even at room temperature, nothing is truly still. This thermal noise can mimic real signals. So engineers choose materials like ultra-pure fused silica, design suspension fibers to dissipate energy gently, and shape components to shift vibrations outside the detection band. They don't eliminate noise, they relocate it out of the frequencies where gravitational waves live. Now consider the laser itself. If its frequency drifts, your ruler changes length while you're measuring with it. That's unacceptable. So LIGO's laser is locked to ultra-stable reference cavities. Feedback systems constantly correct tiny fluctuations. Stability exceeds 1 part in a trillion. At that level, the laser becomes less like a light source, and more like a metronome for reality. When engineers say LIGO is never locked, they don't mean it's unstable. They mean the opposite. The system is always adjusting. Sensors continuously monitor alignment, phase, and position. Controllers make microscopic corrections every second. This keeps the interferometer at peak sensitivity, maintaining optimal interference conditions. LIGO isn't frozen in place. It's alive. A machine in constant dialogue with physics. But detecting data isn't enough. You have to know it's real. Raw LIGO data is dominated by noise. Environmental sensors track vibrations, temperature, electromagnetic fields. Algorithms subtract known disturbances. Then scientists compare the signal against predicted waveforms generated by numerical relativity. And crucially, two detectors must see the same signal at nearly the same time. Chance noise doesn't synchronize across continents. Space-time does. September 14, 2015. Both detectors lit up. A short chirp. Two black holes merging 1.3 billion light-years away. Orbiting faster and faster. Then colliding, converting mass directly into gravitational energy. For a fraction of a second, space-time itself rang, and humanity listened. This wasn't just a detection. It was confirmation of general relativity. In one of the most extreme environments imaginable, it opened a completely new window on the cosmos. A universe we don't see. But here, LIGO proved that with enough precision, even reality's quietest whispers become measurable. LIGO isn't powerful because it's large. It's powerful because engineers learn to respect limits. Noise, motion, heat, imperfection. They didn't overpower nature. They cooperated with it. Layer by layer.
Glad you stayed to the end. That means your curiosity's alive and kicking. If you're into this vibe, like, subscribe, and tap the bell for more mind-bending moments. And don't leave yet. Pick the next video and keep the spark going. See you soon.